The paper of the day is Overcoming CAP with Consistent Soft-State Replication. CAP explores trade-offs between consistency, availability, and partition tolerance, concluding that a replicated service can possess just two of the three. The theorem is proved by forcing a replicated service to respond to conflicting requests during a partitioning failure, triggering inconsistency. But there are replicated services for which the applicability of CAP is unclear. Here we look at scalable soft-state services that run in the first tier of single cloud computing data center. The puzzle is that such services live in the single data center and run on redundant networks. Partitioning events involve single machines or small groups and are treated as such as node failures. This CAP proof doesn't apply. Nonetheless, developers believe in generalized CAP fork theorem, holding that scalability and elasticity are incompatible with strong forms of consistency. We present a first-tier consistency alternative that replicates data, combines agreement on update ordering with amnesia freedom, and supports both good scalability and fast response. One can approach building protocols that replicate data optimistically and later heal any problem that arise, perhaps using gossip. Updates are applied in the first tier but then passed on to inner tier services which might apply them in different orders. One can build protocols synchronized with respect to membership changes and with a variety of ordering and durability properties. Example, virtually synchrony also in-memory versions of Paxos, where Paxos durability guarantees applies only to in-memory data. Amnesia freedom is achieved by enforcing a barrier prior to sending a reply to the client request with the system 4 pauses, delaying the response until any updates initiated by the request or seen by the request through its reads have reached all the replicas and thus become stable. If all updates are already stable, no delay is incurred. One can implement a strongly durable state machine replication model. Most implementations of Paxos use this model. In our target scenario, of course, the strongest form of durability are just meaningful. There's no benefit to logging messages other than in memory of the replicas themselves. One can implement database transactions in the first tier, coupling them to serialization order used by inner tiers, for example, via true multi-copy models on the asset model or a snapshot isolation model. This approach is receiving quite a bit of attention in the research community. Looking at the contributions, CAP is centered on concerns that asset database model and the standard durable form of Paxos introduce unavoidable delays, focusing carefully on the consistency and durability needs of first-tier cloud services. Paper has shown that strong consistency and a form of durability we call amnesia freedom can be achieved with very similar scalability and performance to today's first-tier methodologies. Authors' approach would also be applicable elsewhere in the cloud. Obviously, not all applications need the strongest guarantees, and perhaps this is the real insight. Today's cloud systems are inconsistent by design because this design point works well for the applications that earn the revenue in today's cloud. The kinds of applications that need stronger assurance properties simply haven't yielded enough market power to shift the balance. The good news, however, is that if cloud vendors decide to tackle high assurance cloud computing, CAP will not represent a fundamental barrier to progress.